Taking a look at periodic trends for Unit 3, last lesson of Unit 3. Of course, let's go over our learning targets and see what we're going to be expected to know. Be able to identify periodic trends through the position on the periodic table. The main trends we'll be looking at are ionization energy, atomic and ionic radii, electron affinity, electronegativity, reactivity of metals, and reactivity of nonmetals. We're going to be able to predict and estimate values of atomic properties using periodic trends in the absence of data. So what does that mean in the absence of data? This is very qualitative. I'm going to be able to tell that this particular element's atoms are bigger than this one in terms of atomic size or radii. So you'll be able to predict them qualitatively using the trends. And then we're going to explain the trends using Coulomb's law. Now, you're not actually going to define Coulomb's law as an equation, and it's used in physics. We don't actually calculate anything with it in AP Chem either, but we use the concept of what you were just doing in that POGL the day before, of looking at the magnitude of the charge, like how many protons are there, over the distance, looking at the distance, and those two factors together determine the force of attraction. So the force of attraction, of course, whether it's high or low, whether it's a really strong force of attraction or a weaker force of attraction, really is going to be what determines these trends. So we're going to apply those concepts here. We're also going to be looking at the shielding effect, and that's created by the distance factor, the effective nuclear charge, which is created by those proton numbers, and then the shell model, which also looks at those principal energy levels. So we're kind of combining all of that together for our explanations of the trends. So what is periodic law? Periodic law isn't really a trend, but it's basically stating that when you arrange the elements in order of increasing atomic number, so Moseley went back and redid the periodic table by atomic number, it shows periodic repetition of patterns of chemical and physical properties. So this repetition in their physical and chemical properties kind of goes along with the atomic number, and that's how, it helps organize the groups and other things like that. So the general trends we're going to be looking at because of periodicity and periodic law by arranging them by atomic number. We'll be talking about shielding effect, atomic radius, ionization energy, electronegativity, and electron affinity. Now, the other two, the reactivity of metals, reactivity of nonmetals, kind of falls under the category or umbrella of ionization energy. So we'll be addressing those after we talk about ionization energy. So let's go back over those two major factors that explain the periodic trends. The first one has to do with those number of protons, and we call it effective nuclear charge. It's abbreviated with this ZEFF, okay? It's like Z effective here. Now, Z, when we talk about Z, or the letter Z, we're really referring to like number of protons or atomic number. So when we're looking at Z as that type of letter variable, we're referring to atomic number. And what is effective nuclear charge? It's basically a measure of the strength of the attractive force, going back to that lovely word, attractive force, of the protons in the nucleus minus the repulsions of the core electrons. That's getting a little bit in depth, and we're not going to calculate effective nuclear charge, although there is an equation for it. So in general, this is what we're going to refer to right here. This is the important part. In general, as the number of protons increase, number of the protons increases, the effective nuclear charge increases. So as you're going left to right across a period, you're adding more protons, your effective nuclear charge is increasing. So that's important there. This is the first factor that's going to explain all of the trends that go across a period. The other one, the distance of the valence electrons from the nucleus by adding more principal energy levels or shells. So this is your second factor here. And this is going to explain our trends as we go down the groups. As we go down a group, the attraction for the nucleus is reduced. It's reduced as the outer electron, or that valence electron, is farther away. It's shielded and repelled by core electrons in the inner principal energy levels. So if we're looking at this diagram that was in our POGL activity, n equals 1 here, n equals 2. So lithium has 2 principal energy levels. So it only has one set of core electrons. The first energy level here is its inner core electrons. It has 2 in there. So those will repel this valence electron just slightly. Distance is not very far away, though, from the nucleus. Whereas sodium is n equals 1, n equals 2, n equals 3. Now it has 2 shells, or 2 principal energy levels of core electrons that are going to repel. It's also creating more distance between the outer valence electron and the protons in the center of in the nucleus of the atom. And then, of course, as you see potassium, you just now you have n equals 4 out here, farther out, more distance, more shields, more of these inner core principal energy levels. That's going to do some repulsions. Therefore, the force of attraction from the nucleus in potassium is less than, say, lithium up here. Distance greater, more shielding due to the more principal energy levels. So this is the trend, or this is the explanation for why the trends happen going down a group. So shielding effect, what is it? So you're gonna have to know the definitions of each trend too, like what is shielding effect? Shielding effect happens to be a decrease of attraction between the nucleus and valence electrons because of the presence of core electrons from inner principal energy levels. So it's really what we were just talking about here. We have here 3 energy levels. So this electron is a core electron, and it would shield one that would be out here in the 3rd energy level. So it would lessen the force of the nucleus on, the attractive force on this electron that would be out here in this particular energy level. Now for the trend part. When you move left to right across a period, shielding effect stays the same. It does not change. Now let's talk about why it stays the same. Because as you go across a group, the principal energy levels within the period remains the same. So if we're talking about, so period 2, which is what? Lithium, beryllium, and then it's boron, carbon, nitrogen, oxygen, fluorine, and neon over here. This would be, n equals 2, period 2. Well, all of them have 2 energy levels. So they all only have 1 core energy level, which would be energy level 1, that would do the shielding or repelling. So anything in the same period, pretty much, they might be slightly different, but for the most part, remains the same. So electrons are the same distance, okay, because they're in the same energy level, from the nucleus with the same amount of electron repulsions from inner energy levels. And that's why the shielding effect would remain the same. Now going down the group, shielding effect actually increases. It goes up. Now I'm sure you can see that this is group 16 over here. Here's oxygen, sulfur, selenium, tellurium, and polonium. As you see the Bohr models drawn here, the addition of the rings, of course, increases the distance, increases the number of core electrons that will be repelling, adding some repulsive forces to the outer electrons. Trend is caused by adding more distance from the nucleus by adding more principal energy levels. Oops, sorry, I didn't mean to go that fast. Adding more distance from the nucleus by adding more energy levels. There does increasingly have 4 shields. This would be 1, 2, 3, 4 shields, with the outer energy level being 5 here. This one would be outer energy level 6. So this one has 5 shields. Farther distance, more repulsive forces, lessens the pull of the nucleus, lessens that attractive force. Now, your turn to practice. Which element has more shielding? And for periodic trends, you definitely want to have a periodic table out. So here you find your 2 elements. We have sodium and we have cesium. And a lot of times they're arranged where they're in the same period or in the same group. But which element's going to have more shielding if we're following the trends? Definitely, cesium's down here. This is principal energy level 6. This would be principal energy level 3. Sodium's in row 3. So cesium has a lot more distance, has a lot more core principal energy levels. So yeah, cesium would be the correct one there. Which element has more shielding? Is it going to be carbon or oxygen? Once again, locate them over here on your table. Take a look, find them so that you can compare them where they are. Which one's going to have more shielding? They're the same. Good. Somebody figured that one out. That's the trick question, right? They are the same because they're both in principal energy level 2. So they have the same number of core shields, same distance. So they would be the same. Exactly right. They're the same. Now, atomic radii. This is the given definition. I don't necessarily think about it this way, but it's the given definition. The measure of the distance between two radii of 2 identical atoms of an element divided by 2. I know, seems silly, right? Okay, but basically it's like the radius of the atom. From the nucleus out to the outer electron cloud, what's the distance? What's the size? Any direction. So here, looking at chlorine, they put the 2 together, they measure this diameter here. They come up with this 198 picometers. And if you don't remember picometers, 1 times 10 to the 12th picometers equals 1 meter. It's a very, very, very small measurement. So they decided that take this divided by 2, 1 chlorine atom's radius would be approximately 99 picometers. Now, if you look at carbon over here, this example, 154, divide that by 2, you get 77 picometers. Well, it is smaller in size, which would make sense because carbon's in the second row, energy level 2, whereas chlorine's in energy level 3. So obviously chlorine is going to be a bigger atom. It has more principal energy levels, so the cloud's going to be bigger. That is how it's calculated. You don't have to calculate it, but this is the basic definition of atomic radius. Now, what you do need to be able to know is when I say atomic radius, I'm really talking atomic size, or when I say atomic size, I'm talking atomic radius. They basically are synonymous with one another. Now, trend. As you go down the group, the atomic radius increases. I'm sure you probably could have figured that out because you're adding more energy levels and creating greater distance, more repulsion. All right, those shields with those electrons do some repelling, which lessens the attractive force of the protons in the nucleus to these valence electrons. I like this graphic over here, though, because it's showing this. These are the alkali metals. This is group 1. 3 electrons, 11, 19, 37, 55. So as you can see, as you're adding more electrons, you're getting bigger. Makes sense. They're putting the figures over here in nanometers, and remember nanometers is 1 times 10 to the 9th. nanometers equals 1 meter. So really, if we wanted to compare them in picometers, we can move it over to the right. So 157 picometers compared to 272 picometers for cesium. But it makes sense that cesium would be the largest and lithium would be the smallest in terms of the number of principal energy levels and also the number of electrons. Moving left to right across the period, atomic radius decreases. Goes down. Now let's think about this. Why would that be? As I'm going across the period, I'm adding more protons. Adding more protons means my effective nuclear charge is increasing. So each successive element has one additional proton. So the attractive force of the nucleus increases, pulling the electrons in closer. And as you can see, as you're going across the period, look at the little circles. They're getting smaller as we go across. And helium actually happens to be the smallest element on the table, just so you know. And you can see as you go down the group, it kind of looks like the snowman idea. Increases as you go down. It's like the fallen over snowman going this direction though. So across the period, it decreases. Going down the group, it increases. So snowman, snowman. You can use the snowman analogy if you like. So it's kind of helpful to think about it in terms of the circles. Now, practice time. Go ahead, take a moment, find your elements, and we will come back and answer these. Okay. Which is bigger, sodium or potassium? Well, I kind of just gave it away for you, but yes, potassium. You see as you go down the group, we're in energy level 4 versus energy level 3. Obviously, going down would make potassium bigger. Now let's look at sodium versus magnesium. Yes, sodium would be bigger. If you think about it, sodium has 11 protons, whereas magnesium has 12 protons. That additional proton pulls in the electrons just a little bit, so it's going to be slightly smaller than sodium. Now, which is smaller? Because they can always ask it the other direction. We're looking over here at phosphorus and chlorine. Which one's smaller out of those two? Anyone? Yes, chlorine, good. Chlorine is smaller than phosphorus. Phosphorus has 15 protons, whereas chlorine has 17. So those extra 2 additional protons pulls it in slightly, so chlorine would be smaller. Exactly right. All right, let's talk about cations. Anybody remember what cations are? What's a cation? Positive ions, yeah. So that means what did they do with their electrons? They lost electrons. Very good. Okay. So cations or positive ions are smaller than their parent atoms. Basically, the formation of a cation involves the loss of the outer shell or the outer energy level. So obviously, it's going to shrink if you're losing an energy level. So cations lose electrons, don't forget that part, and they're going to be typically metals. Remember, the metals are the losers. They lose electrons. When comparing, here's the neutral lithium atom right here. When lithium loses the 1 electron, you can see a huge decrease in size from 1.52 to 0.6. All right, and this is in angstrom, so this is 10 to the minus 10 measurement here. But as you can see, the parent atom is much bigger than the ion of the cation here. So these are the alkali metals. This one be the alkaline earth metals where they lose 2 valence electrons because they have 2 valence electrons, so they're going to form +2 charges in order to look like the nearest noble gas and be stable. And as you can see, goes from 1.11 to 0.3. That's quite a loss in size. Aluminum, even more here, looking at, this is group 13. Starts with boron at the top, but I told you like boron doesn't typically form ions, so as you see, it's not on this table. But aluminum, gallium, indium, as you can see, they lose their 3 valence electrons and become cations, and they are much smaller than their original neutral atom or parent atom. Now, anions. How do anions form? What do they do with their electrons? Gain, very good. Okay, so anions, if they're gaining electrons, they should be larger than their parent atom. So that's what we go here, larger. Involves the addition of electrons into the outer shell. You're adding to your cloud. By adding to the cloud, though, you're causing a little bit more repulsions between electrons. And those repulsions, of course, are going to have them spread out, be farther apart. Spreading out farther apart, of course, is going to increase the size of the cloud, thus increasing the radius or the size of the cloud. Now, if we're looking here, this is the nitrogen group, group 15. So we have the nitrogen atom versus nitride, which is the ion of nitrogen, where it gained 3 electrons. Now, remember, nitrogen group has 5 valence electrons to start with, so they gain 3 in order to look like the nearest noble gas. And as you can see, quite a dramatic, jump in size. Here's the oxygen group, or group 16, same thing between them. And then the halogens right here, where they're gaining 1 electron, they get bigger here. Going from adding electrons to the cloud, causing more repulsions, then you get a little bit farther distance. Now let's talk about the trends. That was a trend between the parent atom and the ion. Now let's look what they look like as you go down the group or across periods. Both cations and anions increase in size as you go down a group. So when we're talking about increasing in size, we're looking at the ions of alkali metals, and we're looking at this group only going down. As you can see, if they were all their cations, they are increasing in size. Same thing over here if we're looking at anions, like the oxide, sulfide, selenide, and telluride group here. This is group 16. As you go down the group, you're adding 2 electrons to each. They have 6 valence electrons, so add 2 to, get the 8, the octet, look like the nearest noble gas. Go down the group, they get bigger. Now, ionic radii decrease across a period, just like in regular atomic radius trends, but we're not going to compare every group together here. So when we're looking here at this particular idea, we're going to compare like the cation side over here versus the anions over here, because obviously you wouldn't go across the entire period. The cations, though, lithium's bigger than beryllium, sodium's bigger than magnesium, magnesium's bigger than aluminum. As you can see, it definitely is decreasing as you lose more electrons. If we're just comparing the anions over here, nitride, oxide, fluoride, as you can see, their radiuses are also decreasing. And it's going to be because adding more protons increases effective nuclear charge, increases the attractive force of the nucleus. So that's why these are getting smaller as you go left to right in the anion section. It's why it's getting smaller as you go in the cation section. But you wouldn't want to try to compare beryllium with oxide, because they are 2 different species. One's a cation, one's an anion. All right, your turn. Take a look at these. Place the following in order of increasing size. Now don't forget increasing, like increasing trends versus decreasing trends. Increasing means you're starting smaller and getting bigger, okay? Decreasing would be you start bigger and go to smaller. The reason why I say this is because people easily get confused. So increasing, you start smaller, go bigger. Okay, so increasing size, which one's going to be the smallest out of those three? Chloride, good. So chloride, and you can use like the less than sign. Then out of phosphide and sulfide, which one's going to be in the middle? Yes, sulfide and then phosphide is the largest. Now let's think about this. This one has 17 protons, this one has 16 protons, and this one has 15 protons. So obviously chloride has the higher effective nuclear charge and will pull them in closer. So that's smaller, whereas phosphide has less protons, so less attraction, that they would spread out more. And here is the explanation if you need to go back to it. All of the ions have 18 electrons. Let's think about that too. They all gain enough to look like argon, which is the nearest noble gas. So look at the proton number. Phosphide has 15, sulfide has 16, and chloride has 17. Chloride has the greater effective nuclear charge, so it's going to be the smallest of them. And when we say they all have 18 electrons, they all mimic argon's configuration in order to be stable. The term is isoelectronic. Iso, of course, meaning same, so they have the same number of electrons, basically, is what we're going for, and they have the same electron configuration. So chloride, sulfide, and phosphide will all have the same electron configurations as argon. Ionization energy. The energy required to remove an electron from an atom. So there's the definition. Definitely know this. This is basically the formation of a cation. Energy required to remove an electron. Now, as you move down a group, the ionization energy decreases. As you move down the group, it decreases. Now we're going to talk about, you'll probably understand why, because like I said, the reasons now are becoming repetitive. As you go down the group, you're adding more principal energy levels, creating a farther distance, more shielding, less attractive force from the nucleus. Same deal here. Farther distance, more shielding, more principal energy levels lessens the attractive force from the nucleus. Okay, it's required to move those valence electrons. So as you can see here, these numerical values, like this is 375.7, okay, versus 1312 for hydrogen. As you go down the group, you see those ionization energies decreasing. Now, what you'll also notice over here in the nonmetal section, they have higher ionization energies, but still, as you're going down the group, even if we're talking about helium versus xenon, even though they're much greater numbers than, say, the alkali metals, they still decrease as you go down the group. It's easier to remove from xenon than it is from helium, which actually requires quite a lot of energy. Now, we know these guys are cations. They like to lose. Group 1 does +1, group 2 does +2, this one does +3. They like to lose electrons, so their ionization energy values are typically lower. Then over here on this side, which we know these guys end up being the gainers, where we have -3, -2, -1, and then 0. All right. So the gainers over here typically have higher ionization energies. So left to right across the period, ionization energy increases. Increases. Why? Because you're increasing the proton number, which is increasing effective nuclear charge, which is increasing attractive force for those valence electrons. They're going to hold on tighter. When they hold on tighter, stronger attractive force. it takes more energy to overcome that force. So that's why the energy numbers go up for the nonmetals over there to the right, and especially for those noble gases have particularly high ionization energies because they're already stable. They certainly do not want to give away an electron. So they've really hot, you have to meet a high threshold of energy in order to overcome and create an unstable element that's already stable. Now time to practice. Which element has higher ionization energy? So first thing, hunt and peck, find your elements. We've got magnesium, we've got calcium right here. Nicely grouped together. So which one has higher ionization energy? Yes, magnesium definitely. It is smaller atom, less distance, stronger attractive force for those outer electrons. Which element has a higher ionization energy? Now we're talking aluminum versus sulfur over here. Higher ionization energy. Sulfur has 16 protons, whereas aluminum only has 13. Sulfur's going to hold on to that a little tighter. Need more energy to remove an electron. Which element has a higher ionization energy, cesium or barium? Cesium and barium are down here next to each other. Yep, barium, and that's the same reason as the sulfur. It has one more proton than cesium, so it's a little bit stronger. It's going to hold on a little bit tighter. That also is reason why cesium's more reactive than barium, because cesium's more readily able to give up that electron than barium, and so it's just slightly more reactive. Let's talk about successive ionization energies. Now, what does that mean, successive? Here they give you this data table here, general increase. Now, this I1 means the first electron to be removed. This means the second electron to be removed. Third electron to be removed. So now we're not just only concentrating on removing one electron, we're seeing how it looks, what the pattern is as we're removing more electrons from one particular atom. This would be the fourth electron right here to be removed. And then I5, you know, is going to be the fifth electron to be removed and so forth. What you should notice, though, is look at the actual numerical values, looking at the data. What you're going to see here, especially like looking at, say, aluminum here. The first electron to remove is 580 kilojoules per mole. Not that much. This is usually kilojoules per mole, by the way. To remove the second electron, it goes up a considerable amount, about 1,300 kilojoules per mole. To remove the third electron, it goes up like another almost 1,000 kilojoules per mole. But the second you step over to that fourth electron, it doesn't go up 1,000 or 1,300. It goes up by like 9,000 or 8,000. It goes up dramatically. There's a huge jump in the amount of energy needed. The reason why that is, it requires much more energy to remove core electrons than it does valence. Because remember, as they're removing valence electrons, for the metals at least, that helps them establish stability by looking like a noble gas. As you start removing core electrons, now you're creating instability because now it's no longer looking like a noble gas. You can also see trends down here in the nonmetals. You know, as you can see, they have much higher ionization energies to begin with because they don't typically like to lose electrons. They like to gain them. And then you get over here to where you're breaking with and pulling off. So phosphorus has 5 valence electrons. You pull off that core, though, goes from 6,000 to 21,000. It's a huge jump. Much larger jump to remove core electrons. Now, what does a problem look like where we're looking at successive ionization energies? So we're looking at this first practice example. Ionization energies of an unknown element X are listed in the table. Element X is a member of which group? So what is this data providing for me? I'm looking at, here's the first electron, second electron, third electron, fourth electron. I look at the numbers here. Where does the huge jump take place? Which electron, in between which electron does it end up becoming an absorbent amount of energy? Yeah, between third and fourth here. So what that tells me is this one's still a valence electron, but this one right here happens to be a core electron. So how many electrons, valence electrons, does X have? How many valence electrons? It has 3. And which group do we know has 3 valence electrons? 13 has 3 valence electrons. Very good. Now, we go over here, we look at group 13, 3 valence electrons, and then we can select our answer. So always refer to the periodic table, it's helpful, you know. Remember, this is group 1, has 1, 2, this one has 4, 5, 6, 7. Neon has 8, don't forget helium is strange and has 2 valence electrons. So you can use the periodic table there at that point. So it's using the data in the table to figure out what group are we working with here. Now let's look at it from one other angle. Let me pull up that periodic table just so we have it in front of us. The ionization energies of an unknown element X are listed in the table. We kind of already know that. Which of the following represents an electron configuration that corresponds to the valence electrons of this element? Well, how many valence electrons does this particular element X have? If we're looking at this data, where does the major jump occur? Yes, between 5 and 6 here. You go from 9,000 to 53,000. That's an incredible jump. So the 5th versus the 6th. And this is going to be valence, whereas this one's going to be a core. Now, if I have 5 valence electrons, which group am I? Group 15, right here. Good. 5A, 5 valence electrons. Now, can I figure out the valence configuration? We're going to always fill 2 in the S here. Doesn't matter which row, so NS2. How many are going to go in the P? Five valence electrons, so this is NP3. Good. 1, 2, 3. So which one is my valence configuration? It's going to be C. Good. Exactly right. So look for the jump, then you can tell the number of valence electron, then you can tell the group member, you can figure out the valence configuration. These are the type of questions you would see here. All right, reactivity. What is the trend going down the group for metals? Well, it increases in reactivity typically. Why? Lower ionization energy, less energy required to remove the outer electron. Following the reasons as why ionization energy is lower is because of the distance, the more principal energy levels, the more shielding, which lessens the attractive force of the nucleus. So it's not being held very strongly and more easily removed as you go down the group. So as you can see here, looking at that alkali metal group, even these alkaline earth metals, as you go down, they definitely get less. Okay, now the transition metals a little bit different. Some of them follow the trend, some of them don't, but for the most part, we give it the generalized trend. As you go down the group, the ionization energies are decreasing and the metals are becoming more reactive. Now, what is the trend going across a period? Well, it decreases in reactivity. Basically, as you decrease in reactivity because you have a higher ionization energy increases when you go across the period. That's because you're adding more protons. You have a stronger attractive force of the nucleus, so it's going to hold on to those electrons more, and they're less likely to react because electrons are what's reacting here when we're creating chemical compounds. So if you have a higher ionization energy, it is less likely to react than with a lower ionization energy. Higher ionization energies indicate a stronger attractive force, whereas lower ionization energies indicate a lower attractive force. Higher attractive force is usually by an increase in effective nuclear charge in protons and less distance, whereas the lower ionization energies are going to be because of greater distance, more energy levels, farther away, less protons. Like I said, I become a broken record here. I keep saying the same thing over and over again because they apply to all of these trends. But as you can see, as you're going across increases, the values are increasing, basically holding pretty much a lot truer than the other one, but generalized trend, like zinc is less reactive than calcium, potassium, even, copper there right next to it. Electronegativity. Let's talk about this concept. Now we use this as an abbreviation, EN, as you see here. It's much more easier to write EN than write out the full word. It is quite a long word. The measure of the attraction of an atom has for electrons in a chemical bond. In a chemical bond, the atom with the greater electronegativity is more strongly attracted to the bond's electrons. Now, a couple of characteristics of things with high electronegativities. They're usually smaller atoms with a high amount of protons. So as you move down a group, electronegativity decreases. Why? Because the addition of more principal energy levels creates larger distance, more shielding, and reduces that attractive force of the nucleus. So once again, repetition here. Moving left to right across the period, electronegativity increases. Why? Because you're increasing the nuclear charge, adding more protons as you go across. Same deal, same reasons as all the other ones. Now, let's look at the electronegativity values. This is called the Paulding scale. You don't have to memorize this. If we ever wanted you to use these values, we would provide you with the table, so not to worry there. Looking here at our periodic table, what you see, yes, increases this way, decreases as you go down. So increases as you go up and to the right, basically. Now, if you're looking here, which element is the one with the largest electronegativity value on the table? Who sees it? Which one's the one with the largest? Most electronegative element on the table. Fluorine, good. Here it is, here's fluorine. Oxygen's a close second, but fluorine is the highest. It is the most electronegative element on the table. Now, what is missing from this table? We have something missing here that we should think about, and think about why is it missing. What isn't going to have electronegativity values? What shouldn't have electronegativity values? Yes, the helium or neon or any of those noble gases. Why wouldn't they have them? Are they seeking electrons? Do they need electrons for stability? No, they're already stable. So, noble gases do not apply to this trend. Noble gases do not have electronegativity values. Their values would be 0. And that's because they already have a full octet and they're already stable. So, don't want to bond with anything. Already stable, noble gases, not on this table. So you would exclude them from this trend. You would not incorporate noble gases. So let's take a look here and see what we get for our practice. Which element is more electronegative? Following our trends and things over here. Fluorine and neon. Which one's more electronegative? Yeah, it would be fluorine. This is the trick question. Because we just said noble gases don't have electronegativity values. So that one could be like this is the trickiest one of the periodic trends. Yes. Yep. And then the other one is there's no shielding effect stays the same across a period. So those are the two tricky ones. Which element is more electronegative, sodium or potassium? Here's sodium, here's potassium. Taking a look there. Which one's more electronegative? Sodium, very good. It goes up and to the right. Yeah, it increases. Very good. Which is more electronegative, tin or iodine? So here's tin. Here's iodine. Down there in the same row. Definitely iodine. Good. Exactly right. You're getting the trend here. All right, just two more little things and we'll be done. What is the trend as you go up the group for reactivity of nonmetals? What is the trend as you go across the period? Well, as you go up and to the right, the reactivity of nonmetals has a tendency to increase. Now let's talk about why. As you go up and to the right, you're increasing the electronegativity. Why does the electronegativity increase? Because those atoms are smaller and they have more protons for their size. Like smaller atoms with more protons is going to have a stronger attractive force for electrons. So it is the combo that electronegativity is increasing, and that's really due to like you have more protons, but you have less energy levels in smaller size. That's why fluorine has the highest electronegativity because it has 9 protons, but only 2 energy levels. So it has a really strong positive force seeking out those electrons. Same thing with oxygen. It's only 1 proton less, 2 energy levels, 1 proton less. That's why oxygen is a close second to fluorine. And that's why, you probably hear of all this stuff when it rusts and reacts with oxygen and it's corrosive with oxygen. Well, oxygen's highly reactive and it's going to combine with lots of things while it's in the air. And that's because it is very electronegative and very reactive. Last one here is electron affinity. Really all you have to know here, if you know electronegativity, you know electron affinity in terms of the trend. The definition though is a little bit different. Electronegativity is like the attractive force for electrons in a bond. Here, the amount of energy kilojoules per mole released when an atom gains an electron. So the definition of this is kind of opposite of ionization energy. Ionization energy would be removing an electron. Here we're gaining an electron. Well, the halogens over here have higher electron affinity numbers because they want to gain electrons in order to be stable. So those values, they release a lot of energy in that process. It puts them in a much lower energy state, makes them very stable. What you'll notice here, though, the noble gases, all of their electron affinity values are positive and are very much higher. So in order to gain an electron on a noble gas, you have to really force it with energy. Like it doesn't want to do it because it's already stable. So that's why we would say electron affinity values don't really apply to noble gases either because they're not looking to gain electrons. They're already stable. So this one pretty much follows the exact same trend as electronegativity in that respect. So same reasons, all of that. I'm not going to go through the reasons one more time because we've hit that so many times today. Now, this is the summary of the trends. So put this on here and I starred the ones in blue, of course, that do not really apply to the noble gases, right? Because they're inert, they're unreactive, they're already stable. So electronegativity, electron affinity, and nonmetal reactivity do not apply to the noble gases. You can abbreviate these two. You don't have to keep them, like you could do EN for this, IE for ionization energy, EA for electron affinity, and NR for nonmetal reactivity. Over here, you could abbreviate atomic radius AR and metal reactivity shielding effect if you don't want to write out the entire words. Now, when you're taking your quiz next week and working on your WISER this week and stuff, I would have this thing out. Why? Because it's a coordinate plane idea of kind of organizing all of the trends together. And they put the snowman type circles on there to help you as well. But the ones in the quadrant over here, the upper corner, all of them increase as you go up and increase as you go to the right. So increase as you go up, increase as you go to the right. Of course, those three don't apply to the noble gases, right? Those three. If you look at this quadrant over here, atomic radius and nonmetal reactivity, they increase when you go down and to the left. So left and down, these guys are increasing. And then, of course, shielding effect only increases as you go down. And remember, it stays the same across. So that's why we put it down here at the bottom of this one. And what I would say normally if you were in school and, you know, everything was an open note, I would tell students to write this coordinate plane on the beginning of their quiz or test, right when they get started, so they have everything organized and can remember the trends. So this is a nice tool of kind of putting all of the trends together. Now, definitely go back and study, like, what is each thing? Like, what is atomic radius? What is ionization energy? What is electron affinity? What are those definitions? Like, what is that property? Know what the property is, and then know which way it goes, and then know the reasons why. But the reason why across the period is always because you're adding more protons, more attractive force, more effective nuclear charge, and then going down the group, it's always about more distance, more energy levels, more shielding, lessens the attractive force of the nucleus.